and get started. I'm Aaron Huang. I'm a PhD student at the University of Alabama. I also work at NASA Marshall. And with me is the PI of ASSET, Dr. Sood at the University of Alabama. We'd, of course, like to also thank the other members of the lab, the Astrodynamics and Space Research Lab, for the development and continuation of ASSET. And this is a training hosted by the NESC. So specifically, we wanted to thank Heather and her team, the flight mechanics tech discipline team, for pulling this training together and getting a chance to expose what we think is a really great tool to a lot of NASA mission designers and planners, and hope that this is a useful training to kick off an introduction to the tool and get you started to do some good mission design and analysis and optimization solving in the tool. So to start off, you've probably at least heard the term ASSET since you're at the training for it, but ASSET stands for the Astrodynamics Software and Science Enabling Toolkit. It was funded by NASA under a ROSES grant in 2018 for Astrodynamics tools, and it was developed with a few specific software goals. So it is a general purpose optimal control and trajectory design tool. So under the hood, it is a general purpose optimizer with some pretty cutting edge applications of using an interior point optimizer. And then it was built on top of that general layer. There is a trajectory optimization layer built on, so it has extra functionality and is really well tuned for optimizing trajectories, specifically in complex and multi-phase, multi-objective scenarios. The tool is also designed to allow for large-scale optimization trade studies, so parallelism is built in from the start. The tool has quite a few tools for parallelizing everything from integration to even running in parallel trade studies on entire multi-objective optimal control problems. And finally, another thing that helps set ASSET apart is it is entirely open source. So our goal was to minimize compatibility issues and dependencies and have a lightweight toolkit that anyone can use wholesale as is, or is free to add on to, use as part of another tool. And to our knowledge, ASSET's even been brought into, because we're on an Apache 2 license, has been brought into a closed SCIF lab by a DoD contractor at the Aerospace Corp. And the license allows people to do that and develop new tools or bring it into classified research if needed. And it is available on GitHub now, so you can download and build from source from GitHub, or a lot easier, which we advised in the invite to this meeting, because it's hosted on PyPy, you can just do a pip install for asset_ASRL, and that should have a pre-built version that has all the dependencies you need. So there are a few major components to what ASSET is and an overview of what the tool has. The core component, and we're going to do a whole tutorial section on this, is the vector function auto differentiation system. So ASSET's written in a vector function language that allows for analytical automatic first and second derivative calculations to do auto differentiation. So you don't, as long as you can define your optimal control problem in your ODE, you don't need to spend time hand deriving derivatives of your system and your constraints. It has a custom written nonlinear optimizer called SciOpt. It is a dual primal interior point optimizer with location transcription, and it is custom built into ASSET to handle this vector function auto diff system. So it is not numerically approximating your Hessian, for example. It's using the analytical adjoint Hessian of your problems. It has general purpose single and multi-phase optimal control solvers. So if you can formulate a problem in the standard optimal control equation format, it's able to solve that for single objective or multiply scaled multiple objective phases. And then, of course, it has spacecraft trajectory design tools that it ships with so that you can get up and running with astrodynamics problems specifically right away. So Asset is implemented in C++. So under the hood, we're running with compiled speed using things like the Eigen library, Intel's MKL. But then we use PyBind 11 to bind all of that functionality to a Python interface that you've downloaded when you did pip install, for example. So as a user, there's little to no interaction with the C++ code. If you can write in Python and use the library syntax that we've got for Asset, you're able to leverage that C++ compiled speed without ever actually typing or writing scripts in C++. So that's a great way to expose and make the tool easier to use, but still get the advantage of a compiled language. And it makes use of extensive vectorization and parallelization for primarily speed.
You guys compiled the C code. Do you optimize it for the AVX instructions?
Yeah. So the question for anyone online is, when the C code is compiled, is it optimized in how the compilation happens? And yes, it is set up so that you should have very few empty calls going to your processor. So it intentionally packs in your transcription, intentionally packs all of the logic packets that are going to your CPU. So that is part of the secret sauce of its speed. So public usage, Asset was publicly released in December of 22, open source and hosted online. It's gotten significant use in academia and industry already. So it's gotten quite a few peer-reviewed articles, conference papers, and multiple PhD dissertations that it's been used in. And it's gotten some good NASA usage so far also. So everything from ESDMD, so work on Artemis 1 through 5, the Artemis 1 disposal study, human lander tools, and Moon to Mars autonomy study. It's been used by NASA's STMD for the Solar Cruiser mission and for some other Space Force solar sail studies. And it's gotten use by SMD, doing things like the Moonbeam Mission of Opportunity proposal. It'll be used on the MoonCat SMEX proposal, everything through HFOS and MMS follow-ons. So it's gotten used by and has applications for trajectory design problems in lots of different NASA directorates. So let's do an overview of the training of what all we're going to walk through. So this is definitely meant to be an interactive training session. So we're going to introduce in day one Asset's core functionality. The goal of day one is for Asset to not feel like a black box. We want users to understand the core functionality under the hood and to build familiarity with formulating problems from scratch in Asset using its core functionality, things like that vector function type system, ODEs, phases. And then day two, we'll cover anything that we didn't have time to get to in day one. And then day two, we're going to look at the Astro library that ships with Asset, which is essentially a bunch of pre-compiled Astrodynamics specific modeling and frames and models and utility functions. So we're going to do examples and take time to pause and let you code through examples as we go in this, so that you can hopefully dynamically run into any issues and errors now. And please do speak up if you have questions during those examples, and we can work through it and get at the end of each day, you should have a couple of scripts that are running the core functionality that you can reference. So before we dive into that, the first section is running vector functions, but I wanted to check, did everybody have a chance to get Asset installed on their machine? Now is a good time to debug and fix that if not. So everyone in the room has it. Anyone online running into issues getting Asset installed?
Hey Aaron, this is Kaushik Panpali from Glenn. I've had some
Hey,
issues. I've had some issues installing it. It doesn't seem to be available on pip for Mac. Is that still the case?
Ah, okay. Yes. Let me let's see. Mac. We've had challenges with Mac in the past.
Yeah.
Yes. Do you have which CPU you have? Is it the Intel CPU still?
Yes.
Okay. We have it is possible to build on Mac with the Intel CPU. If you have the Apple Silicon, I don't remember which there. Yeah, I don't think we're built for that because of the Intel API dependency. I do think on Mac it needs a build from source.
Okay.
Do you have access to a Linux, remote into a Linux system or a Windows system for today?
I do not.
Okay. Let's do this. If it's okay, we'll keep starting with the training, and fairly early on, there is a demo where people will start writing their code. Would it be all right if I called you on a different channel and we tried to walk through the build process then?
Yeah, that's just fine.
Okay. I know we had this issue earlier. Yeah. Text James and see if he's able to join too. Okay. So I'll meet with Kaushik later to get build from source on Mac. Anyone else online having issues?
I'd also like to be included in that as well, if you don't mind.
Yeah, can I grab the name of who that was?
Yeah, Nate Steffen.
Alrighty.
And can you add me? This is Chuck Rennerson, JPL.
Yes.
Thank you. John Sims is maybe the POC info you have right now.
Sounds good. Okay. So we'll do like a breakout session for that soon and make sure to get those people invited. Hang on 1 second. Are we able to make a separate meeting? Because you folks something separately. Yes. Thank you. Okay, so while that's getting configured, let's let's dive into the first section on the core functionality here. So this first section is all about asset vector functions. You will be using vector functions extensively when you're using assets. So we're going to really want to make sure that that you're comfortable with this type system that we're using, because it is kind of the entry point for any of the more complex operations you'll use in asset. So a key component of vector functions are vector function arguments. So when you instantiate problems in asset, you will use arguments to establish these problems for your inputs. Because remember, we are writing the problem in a Python script, which is dynamically typed. But at the end of the day, you're running your code that will never hit the Python interpreter. It's going to run your compiled C++ code, which is strongly typed and needs size definitions before computation. So when you're doing your imports, you can see on the right side here, you'll normally import asset vector functions as a asset library. And then from that vector functions, for the rest of this training, we do importing from asset vector functions arguments, and we import them as a capital A args. So for the rest of this training, if you see that capital A args, that is a vector function argument that we're instantiating. So all vector function definitions begin by declaring your arguments and deciding the size of your arguments to track their ordering. So the basic example here is if you've got 6 states or 6 inputs to a function that you're trying to run, you will allocate your arguments to be size 6, as you see in the bottom here. So this is callable with both vector functions and with actual value. So don't think of assets vector function arguments as data storage. You are not storing data in a vector function. You are allocating computations. You are setting up future computations. So your arguments themselves are an operator, not a data storage like a NumPy array. So you can even see on the sample code on the left here, we can declare X, capital X is equal to args size 6. It is not a number, it's a vector function. So on the right terminal print, if you try to just print what is args 6, it's not a vector or anything, or sorry, it's not a NumPy array or anything like that. It is an asset object, a Python object. However, these arguments are your input to all of your computations. So real values can get passed through vector function arguments. So you can declare, say, lowercase x vals to be this NumPy array of 0 through 5. And if you print argument 6 and you pass it in with open and close parentheses, you pass in actual values, you can see the next print on the terminal, X is going to return those real values that you passed in, because when you're passing actual data stored values into an argument, then you can evaluate the operations that are allocated to your arguments. So another key component of using the argument system is it starts adding vector function methods to your data operations. So right away, as soon as you set up a vector function argument, whatever you're doing with it, you can compute the analytical Jacobian and the adjoint Hessian of that operator. So you can see, it's as you expect here of a unity identity matrix for your Jacobian and such. But this is just an example of as soon as you define things as vector function arguments, that is an operator that now has some of the asset methods built in. So, it's useful, and we need to partition how many inputs we're sending into all of these functions that we write with vector function arguments. But you're obviously going to want to partition those out further and break it apart into components. So say you need to write functions that do operations on individual components that are passed in, you can use indexing on your vector function arguments to break apart the inputs. So if you've got a function that expects argument 6, and that's x0 through x5, you can still break that apart and do operations just on those individual components. So you can either allocate it with bracket operators, just like you do in Python for indexing, which will pull out a scalar function, an asset scalar function type from that vector function argument. Or you can break that apart using your vector function method toList, which breaks it apart into its individual components. So the result of this partitioning is still not a data storage, or it's not a data storage type, it is an object. So the result, even when you break it apart, is now an asset scalar function, or if you break it into a vector like we'll show next, it is still an asset vector function. So it comes with the benefits that it still has the vector function and scalar function methods appended. So you can see on our code example to the right, we can break out individual inputs of that argument 6, and it still has the method of Jacobians, for example. Sometimes, though, you don't need to just break your argument inputs into individual scalars. Sometimes you're doing data, and actually often you're doing data manipulation and computations that need vectors, so sub-vectors of that full argument input. So assets, vector functions do have built-in methods for partitioning vectors that are sub-vectors of this large arguments input. So the most commonly used ones are taking your vector function arguments and doing head, tail, or segment. So those are three methods built into your vector function arguments that essentially just break out a subvector. So head does a subvector of your arguments of whatever size you input that naturally just goes from the first argument through the size. Tail does the same from the back end, so the last input of your argument structure to whatever size vector. And then segment is how you can pull out vectors, subvectors from your arguments that are not head or tail. So you can say, I want to start at index. In this case, I believe we pull segment index 3 and do a 3 length will result in, for this at 6 input, the last 3 elements. So this is useful for something like a function like an ODE, let's say, which we'll get to later, that you need position and velocity vectors. So you can allocate an argument size 6 because we're expecting 3 position and 3 velocity. And then you can break those components apart into subvectors. So R can become head 3 of that X arguments operator. And now you've allocated, hey, R is an asset vector function constructed of the first 3 inputs to arguments. Same with velocity. You could do tail 3. You can also do standard Python syntax of partitioning if you'd like, of bracket operators, what's your start index, and then colon, what's your ending index. So you can see on the right here, in the code on the right, the R is equal to X head 3 is an equivalent statement as X0 colon 3. For the segment operator, which, again, it's still just pulling out a subvector. Remember, it's now got 2 inputs. It's got the index that you want the subvector you're pulling out to start at, and then the size. So at the very bottom of the code example on the right, n is equal to that argument 6x dot segment 1, 4. That essentially means give me a size 4 vector that starts at index 1 and then is size 4. So you can use those calls almost interchangeably. Remember also for the scalar functions, we had that arguments dot toList. If you pass no arguments into the method toList, it assumes it's breaking your vector function into all scalars. But the toList operator also has the way of passing in an input, and it can break apart subvectors instead. So the toList, if you just call it, returns all scalars of your large X arguments object. But if you want subvectors, you can do that all in one line to save space or be syntactic sugar, to pass into the toList method a list of tuples. And those tuples are essentially the same input structure as the segments. So each tuple is a subvector that you're wanting to break out. And the first part of the tuple is the starting index, and the second is the size. So if we've got an arguments 8 here, where we know the first 3 are the R vector, the next 3 are V, after that is time, and after that is some U control vector, we could allocate it like you see at the top of this, this code snippet, where we're using the head and the segment and Python indexing. Or you can do an equivalent statement that is in one line. You do that large args8 dot toList, so you're using the vector function method of toList, and you're passing in a list of tuples. So we've got a starting at index 0, we want a 3 length, so that gives us the R vector. Starting at index 3, we want another 3 length, that's velocity. At index 6, we want a 1 length, so it breaks apart time as a scalar function. And then same with the U vector. So once you've partitioned this large argument structure into these smaller, it is almost, you can use it as like a recursive call. You can even break these sub-vector functions into scalar functions, or you can break these sub-vector functions into smaller functions. So from those last slides, you saw how to take this large args6 structure and break it into position and velocity. If you wanted just individual components of those subvectors, you can still break those apart even. So, an r.toList is going to return the three scalar functions of that R subvector. And they can be they can be used to lists, they can use head, tail, or segment, or Python indexing. So you have as much granularity of this large arguments section as you want or need for your problem. So we've gone through a lot of introduction to the allocating size of a vector function argument, but so far it's been essentially just boring data storage and understanding that this is an object, not a data storage, but you're going to actually do operations on these vector functions. That's why they exist, is for you to construct problems out of them. So vector functions have standard math operations that you can apply to them, and Asset handles that under the hood of doing computations with whatever gets input to these structures. So you can, for example, take elements or vector functions and you can do multiplication. So the code example on the right, we can see we've got X is that arg6 allocation. We then break that X into position and velocity vectors, so R and V. You can do things like taking individual scalars from those vector functions, so R index 0, V index 0, and 1. You can multiply those scalars together, and you can multiply scalar functions by float points. So you can take any of these vector functions or scalar functions that are Asset object types, and you can do math operations like multiply or divide scalars by them. You can do inverse operations by dividing floats by these scalar functions. And as long as you have proper sizing, your output size needs right, we're not going to break mathematics, you can do vector operations between Asset vector functions. So you can add the R plus V. You can add a 3-length vector function with a 3-length vector function. You can additionally use some of these mathematical operations from the vector function library in Asset, which, remember, we imported that as VF. So vf.sum, you can pass in multiple inputs and sum those components together. You can subtract or add proper sized Asset vector functions from NumPy arrays. So as you can see, there's mixing that you can do of declaring and allocating operations that are Asset vector functions. You're free to do operations to those that are also done by defined data, such as defined scalars or NumPy arrays. We've got a question.
What's the difference between that multiple? They do the same thing, it's just one syntax sugar.
Yes, so the question was on the vf.sum and the difference between just adding. I believe in this example, yes. So in this example, it's syntactic sugar. It's going to be the same result of taking your scalar component addition of your vectors. So you can pass as many as you need into that sum list, and it'll do it on a component by component addition.
And so you say in this example that was true then?
Yes, that is always true.
I mean, so like the way you have this, it kind of implies that the straight addition, they have to be the same size. Is that true for the multiple? They have to be the same size?
Yes, the question was on vector function sizing. You need consistent sizing of your vectors for operations. Totally. Yeah. So VF sum is not a magic sauce. It still needs the consistent vector sizing.
Syntax for
Yes, we will get into that very soon. So if you have a vector that you want to multiply by a scalar, you can just do that. And you can multiply a vector function by a scalar function. That's just the Asset allocation. So you could do like the R vector times index 1 of V for whatever reason if you needed, or you can just multiply it by a float. But vector operations, oh, yes. Oh, good point. So vector operations are an optional. So here's just a list of the standard math functions that are written into the vector function library. So instead of using, for example, NumPy operations, you're going to use vector function operators within these structures that use it. The main reason for that is under the hood, Asset has an auto differentiation type, excuse me, where a lot of these mathematical operators that we're doing, Asset was derived in such a way that the analytical first and second derivatives of operators are built in and compiled in Asset. So if you construct a problem from these compiled vector function operators, you can now do a type of auto differentiation that yields the analytical first and second derivatives of your vector function operations that you're doing. So we're going to use the vector function math library and operators for these things. So anything like doing a sine, cosine, any of your trig functions, we've got it for log or exponential functions, square roots. We use now, when you're writing a vector function or a function that utilizes vector functions, we're going to use the vector function library from Asset to do this instead of, say, NumPy or SciPy, so that we're retaining information, and these more and more complex operations that we're configuring our vector function arguments into can use and leverage the advantages that Asset provides. So once you've defined a vector function, which, for example, again, we allocate arg6 is our input large structure vector functions. Inputs are vector function argument inputs. We break it apart into vector functions by doing like head, tail, or segment. These results here, so R and V, are vector functions. So these vector functions have utility methods built into them that, again, we've got the derivatives analytically compiled into it. So if you need the normal of your R vector, you now have the option of just doing r.norm and calling that method, and it'll compute the the normal or the magnitude of that vector in such a way that's using Asset's vector function type. So you can see on the right here, we've got quite a few vector operations that you can do as a one-line operator. So norm or norm squared obviously is just absolute value of your vector, and absolute value squared or cubed. Inverse norm is going to return a scalar that is 1 over the magnitude. Same with inverse squared norm, which is 1 over the magnitude squared. There's then a normalized. So recall, norm, a vector function dot norm will yield a scalar. So it'll become an Asset scalar function. Normalized becomes a unit vector. So it stays a vector function, but you've normalized it to be unity length now. Then there's also these operators, because in Astrodynamics, you often have things like the R-squared law. There's a way to normalize a vector relative to a power of its magnitude, because normalized is just a vector over its own magnitude. But then there's normalized power 2, power 3, or power 4, which gives the vector divided by its magnitude to some power. This becomes useful, and we'll see very soon. For example, the two-body problem, if you're formulating it, what's your acceleration? It's just negative g times your position normalized power 3, because it's your position vector divided by the cube of its magnitude, so that you're getting a unit vector and then divided by its R-squared law. So these are operators that you'll commonly use once you've partitioned what vector functions you're using. These are ways of doing vector operations. Yeah.
You said that these don't return just like a float or a double or something like that. It returns.
Correct. So the question is, these don't return floats or doubles, right? And the answer is yes. These are still not data storage. These are setting up operations that we're going to run. So just like F, or in this example here on the left, R, is not a data storage. It is a vector function object, the result of running these methods that are appended to it are, again, either an asset scalar function as appropriate, like norm will give you a scalar function, or an asset vector function like normalized. So we're still within the asset vector function type system here until, and it stays that way until runtime, until you actually evaluate whatever operations you've set up.
What is the intent to having all of these functions on the right there that are similar to each other, but just vary by, say, a power, instead of just having a smaller subset that the user can then put together? You know what I mean? Like, why do you need f dot normalized power 5? As opposed to just letting the user write out f divided by f dot norm to the fifth.
Yes. So the question is, why are there these sub expressions that are predefined instead of just stacking operators? And really, it's just shorthand. So you could absolutely just stack operations of, take your f dot norm and then run it through the vector function exponential and then do vector function division. You can do that and you'll get the same exact evaluation. This is just a shorthand of the stack of evaluations that you'll run so that you can still maintain assets first and second derivative computation.
And in the comments here, it says
Yes.
that what it seems like what Adam asked is the same but slower.
Oh, I see.
Yeah.
But it's so that it is computationally slower to do it that way.
It is. Yeah, these are precompiled operators. So these operators have faster runtime because they've compiled their derivatives of these operations specifically.
Have you benchmarked it though? Like, are we talking 1% or 20%?
Yes, if you look at, I think that's in James's dissertation. In James Pezent, so he was the lead dev of Asset. His dissertation has a lot of the asset benchmarking, and yes, so the fastest operation, I don't remember the exact time because it was on the order of milliseconds, but for each function call, I think he did find that the compiled vector function operators were the fastest in his comparison between using Python vector function, C++, and forward auto diff, I believe.
So question
So
there,
I
Aaron.
will defer to that.
So
Yeah.
when this code was built, was it designed with the intent of elevating optimal code up to, say, like the nominal coding level? Is that what I'm hearing?
I don't know if I understand what you mean by
So yeah, usually you have like when you code, you got primitives and things like that, and so like primitives are like kind of the lowest level type of function or things like that or action you could take, and if you elevate those and create more complex ones, you can bring it higher up into the coding, the general coding level for the user who's doing the coding. And is that the intent of the program? Is that kind of like one of the secrets of why it's so fast?
Yeah, when Asset was written, and it's C++ underlying, the code is pretty efficient and leverages common sub expressions. Thank you, James, for pointing that out to me when we were prepping for this. So yeah, the Asset's underlying code is pretty optimized, and then exposed to these precompiled optimized functions are exposed to the user so that you can use the fastest method for doing these things.
But like at a primitive level, you brought a richer set of functions up to a higher level, so that in general coding, if you know those functions, you can pretty much be guaranteed you're writing fast code.
Yes. So yeah, you can, your functions that you use here, as long as you stick within the vector function type system, you can stack these operations, and commonly you are stacking these operations to build one larger complex evaluation. So that's why, even at the bottom, you could do R divided by R3 and this type of computation. It's going to be it's the same evaluation. It's faster because these function operations on the right here in this table are precompiled, very quick operators, with the required derivative information that vector functions need.
Okay, I understand. Thanks.
Yeah, definitely.
So when you said that these functions have analytical derivatives attached to them, let's take the V2, for example, where we have V dot squared norm, and then you have the example of not using V dot squared norm. Is it going to struggle with that because it doesn't necessarily have a defined analytical derivative when you define it that way? When you define it as actually like a sum of squares, is it going to have trouble with derivatives?
So the question was, will asset have trouble with derivatives if you're using these other sub-expressions instead of these precompiled? And no, because it's the type system is written to do essentially sub operations stacked in a proper order. So it can handle the derivative functions as you compile it. As long as you're compiling a problem that has valid derivatives, it'll handle it the same. We just use these precompiled operators because they don't need to stack operators now. They are one operator call that returns the derivatives of this function.
You're using sets built in.
Yeah.
But by doing the vector function under the hood, we probably change this one.
Oh, perfect.
He's got all of this written out.
Mhm.
So if you don't use these precompiled functions, you can still handle it. You're just gonna take it performance.
So that's probably why there's another like it's so much complicated. It's computationally so much faster.
Right.
Yeah, but I mean, it's still C code, so it still gets pretty darn fast.
Yeah.
And in the second case, it's rebuilding the differentiation, right?
Mhm.
It's saying, I don't know any of this. It's going through and rebuilding itself, which is not that slow.
Okay.
Whereas the other one's like, hey, I hard coded it essentially because it's a narrow case.
And with the function on the right, he's got all those derivatives
Mhm.
and all the second derivatives, which is the key when you start doing optimization. Because when you get to decide what's that
Right.
means.
Cool.
Sorry.
No, that was perfect. So if you guys couldn't hear online, that's kind of it was just a discussion in the room, kind of talking on using these precompiled operators because it's compiled with the derivative information already, compared to having to reconstruct the more complex operators like normalizing to a power. Okay, so that was good discussion. Let's look at the next. So vector, we had a question earlier about vector operations. So similarly to how there are vector functions and vector function operators that we went over in that previous slide, there's also a lot of common vector products that you might need to construct a problem or to construct an ODE that are, again, built in the asset's vector function type. So any vector dot product or cross product, any coefficient-wise product, and I believe quaternion product is built into asset's vector function library to handle, again, the analytical operations of what you're trying to do. So if you have a vector function like R, and you have another vector function of the proper sizing that you want to do a dot product with, you can do that one vector function and then use the dot or the cross method that's been appended to that vector function, like you can see in this example here, and then just pass in the other appropriately sized vector function you want to do the operator on. You can, of course, also just do that same operator from the vector function library because your vector functions inherited the method from the vector function library. Excuse me. Same is true for cross products. So you can do R cross V. Again, you need proper sizing. So you need to do proper math operations when doing this. You know, you're going to throw an error if you try and do a cross product of inappropriately sized vectors. But you then can stack these operators. Operations that you need, you've taken a large input structure of vector function arguments, you've partitioned and allocated it to subvectors or scalars, you've done whatever operations you need on them, you then can stack vector functions and scalar functions together into one long output. So for example, in this code snippet, we're defining the RTN frame. So you can have a Cartesian input of size 6. We break it apart into an R vector and a V vector, and then you do the operations you need to get the basis vectors of an RTN frame. So you do R dot normalized, again, using that vector function method that's appended to R, so that you're using the vector function type system. We can do cross products and then normalize. Notice here, the R cross V operator that runs first in this expression, R cross V, a 3-size vector function crossed with a 3-size vector function. The result of this operation will again be a 3-size vector function. So the result has all of the methods appended to a vector function. So you can just do R dot cross V, and then the result of that computation has the dot normalized function. So even doing operations or breaking things apart into sub-expressions, they maintain the methods of their type system. So once you've done something like this, where you've got R hat, N hat, and T hat of the RTN frame, you can now define, hey, here's a 9x1 array by doing VF stack, so the vector function stack, and you can just pass in your components to make one long output. So this is essentially like if you've written an ODE in SciPy or NumPy, where you need to return a single output of all of your derivatives, you're stacking these. The stack function is also written to let you mix type systems. So you can mix in one VF stack, you can pass a float point and then a vector function, then another float point, and then a NumPy array. It's able to handle all of that and then pass out the appropriately sized function that you're combining.
Is this like a Python list sort of you're making?
Say that again, sorry?
Is this like a Python list that you're making? It kind of reminds me of a list.
Yeah.
Accept different types and, create a combined object, I guess. That's a list.
Yeah, very similar. The output is going to be a vector function object. So you're retaining assets vector functionality. Okay. But yeah, very similar to a Python list. And actually, that's a good point you bring up in that your indices for this combined stack will be of whatever size results from all the things you're stacking in. So for example, this stuff vector function that we've stacked, index 1 is this 7.0, and then index 2, 3, and 4 are going to be the scalar components of R hat. And then index 5 is the 42, where it's going to stack all of those together into its scalar components.
Okay, so the first element is not referenced using 0, it's 1.
It is. Sorry, did I say index 1? That's my bad. It would still be index 0.
Okay, thank you.
Yeah, absolutely.
Does it actually put a NumPy array as the final entry, or is it expanded? Kind of alluding that it's expanding.
So the question is on how does it handle that NumPy array? And I believe it's going to convert anything that it takes into the vector function type system. So you can
evaluate. That's not what I mean. So like, if you have, let's say, two things, so you have like the 7.0 and then you have the NumPy array, right?
Yeah.
Is it going to come up with the stuff going to be resultant in length 2, or is it going to be in length 3? As in, it's expanding those elements of the NumPy array into multiple things. Do you know what I'm saying?
I don't know what you mean by expanding it into multiple things.
Well, so like typically when you do this stuff, like we use like frames, you provide a list, right?
Yeah.
That list gets expanded, right? So there's 3 elements in that list, usually what we do. And so there are 3 separate entries into the resultant thing that comes in the stuff, right? So
I get
the question is, like in this, are you going to have like in this particular case, you have let's say R has like one value or something like that.
Mhm.
So it's 1, 2, 3, and then there's 2 elements in the numpy. So
Yeah.
is stuff can be of size 5 or stuff can be size 4.
Yes. Okay. I understand now. So
It
the
automatically expands.
yes. So the question is on essentially the sizing of stuff. And yes, it will break any vector functions you pass in or NumPy arrays will get broken apart to properly size. So in this stuff, index 0 is 7. Since in this case r hat is a size 3 vector function, index 1 is r hat 1, index 2 is r hat 2, index 3 is r hat 3. That same logic of breaking r hat into different indices happens to your NumPy arrays. So yeah,
it's not
one-
analogous. Really expanding
yes.
everything out.
it is expanding everything out into its argument size.
It's the smallest amount.
Into the smallest amount. So yes. So essentially it's not, if you take stuff and you take index, let's see, 7 is 0, r hat is 1, 2, 3, 42 is index 4. If you take stuff index 5, it's going to return the 2.7 of the array. It's not going to return an entire NumPy array. So VF stack, because of that, and a logic behind that is now stuff is a properly sized object. And if you know the size of that, you could even pass those in as arguments of a pre-allocated size to another argument. So you could have this whole code chunk here run and compute the RTN frame and return just a large stack of all of it of size. Let's look at this example here of size 9, but the logic applies similarly to this stuff example vector down here. You could then do another vector function that allocates, x2 is equal to arg size 9, and you could now pass RTN into that size 9. And actually, that's a great segue into the next examples. There's a question about if r hat was a matrix. I believe in stack it will flatten your matrix, and we're going to get on to matrix operations soon as well. Ta-da! Matrix operations. So asset vector function type system does have limited matrix operation support. So it can interpret vector functions as a matrix, but you'll need to allocate it as such. So here is a great example following on from that last slide of how to do that. So RTN coefficients on this side, we are, again, forming the RTN frame of basis vectors. So this RTN coefficients is essentially a 1/9, not a list, it's a vector function, but a set of arguments of size 9. You could then take those flattened sizes and construct matrices of them. So here comes that first decision point when doing matrix operations. You need to choose, are you column major or row major? So essentially, are your, when you look at a matrix, it's actually combining vectors. Are your vectors living in columns or in rows? So we would then compute a column or a row matrix or row major matrix. I would recommend, unless you have a mathematical reason to, constructing it into column major for the reason of matrix operations in asset, the results default to a column major result. So if you're doing row major matrice operations, keep that in mind, that if you do, for example, 2 matrices multiplied together, asset will absolutely handle the matrix operations on the back. You can add and subtract, you can invert and transpose, and you can do matrix or matrix vector multiplication. Just know asset's going to return, if asset's returning a matrix to you, it's going to return it in column major form. So say we take the RTN coefficients here. We've got the RTN basis vectors frame. We want to form a matrix out of it. We can then do, from the vector function library, a column matrix, pass in that essentially 9 by 1 or 1 by 9 structure, and then allocate it by our rows and columns to make a 3x3 matrix. Again, once you've now constructed a matrix object, it similar to how vector functions and scalar functions have built-in methods to their type system, your matrices will have things like an inverse method and a transpose method. Additionally, when you're doing matrix operations, you can't, Asset's not going to handle it if you break math. So if you try and multiply inappropriately sized matrices, it's going to throw an error still. But if you're doing the mathematically proper operations, the asset type system can handle those. So conditional operations, there is limited support for conditionals. You can indeed do a vector function if-else call if you need to do an evaluation. So say you have some condition you want to evaluate, in this case, a scalar function of x0 is less than 1.0. You then can construct essentially what do you want to be returned from this operation if the evaluation is a Boolean true, and what do you want to be returned if the Boolean is false. And then the resultant of that, you use the vector function if-else type and put in your condition that's being evaluated, the results of true and the results of false. And then you can run your operations through it. So here, for example, function is an instantiation of, it is the if-else operator of the condition. It's expecting arguments 3. It's breaking it into 2 lists. So we're breaking it into scalars. And it's saying, hey, if the first scalar is less than 1.0, return the second scalar times 2. And if not, return the second scalar plus the third scalar. So you can see the prints of this evaluation is this first one, it returns true. So it's going to return x1 plus or times 2. And we're passing in 0, 2, 3. So it does 2 times 4 for the true output. And then this next case is going to return a false based on the first input. So it's going to do 1 plus, or index 1 and index 2 added together. So the result is 5. So it has the capability built in to do these logical evaluations. Be very careful to not use these inside operation or optimizers. Asset optimization, if you can avoid it, avoid using conditionals in an optimizer, because your optimizer is using the vector function type system in SciOpt, the custom built interior point optimizer, to leverage analytical first and second derivatives. You've got analytical Jacobians and Hessians that you're using, and the switch point of these conditionals is, I would say, not inherently, it's also just not often a smooth derivative at that switch point. So if you can avoid it, if you need conditional operator, I would suggest using it to construct an initial guess, but don't have a conditional inside of, say, a constraint function or an objective function, which we'll show how to build later.
How is that even implemented? You know what I mean? A conditional operation, the derivative of a conditional operation. What does that even mean?
It's not differentiable. That's why so.
Well, it's not differentiable at the switching point, right, where the operator goes from true to false, false to true. But how would you even implement something like that mathematically? What does that even mean?
Oh, so that's the question is, how is this operating essentially? You've got a switch case here essentially with your conditional.
Right.
And what you should be handing in output true and output false, you can see is constructed from vector function arguments. So essentially you have the derivative operators of if it was true and the derivative operators of if it's false. So if you're always in true, you know the derivative's there, but you don't know analytically when that switch case will happen.
That's what I'm getting at.
And you had a question.
Okay, let's see. Online, is there any error from asset if it encounters? Can you read on the chat. I don't want to hold
Yeah.
up on the full screen.
This is from Rob Falk. Is there any error from asset if it encounters something that's non-differentiable, or will it just power through?
Okay, great question. On does asset throw an error if it hits a non-differentiable? So often it will not throw an error. It will try to power through. So for example, say you are, I've run into an issue before where I wasn't thinking about the vector function type system, and I tried to do a constraint function of an absolute value, but I didn't constrain that absolute value to stay where it's true. So what's the second derivative of an absolute value at 0, you know? So best practice is if you know that there's going to be a subset of your solution that doesn't have defined derivatives, is to use assets constraint operators to constrain your problem to stay outside of that. So for example, if you're setting the optimize the norm function of some evaluation, I will then set the norm of that component that's being optimized. I set it to always be greater than, 1e to the -6 or 1e to the -12, just so I can keep it, the solution space, bounded within an area where the derivatives are defined. So that's a great question.
Thanks.
Yeah, absolutely.
Is there a way to like test your model for non-differentiability? Like, do you have the ability to double check it against any other like complex step or finite difference?
Oh, that is a great question. I believe there is. I'm trying to think, let my coffee kick in and think how to change the evaluation type. One thing that I can do that I know is an answer, and I will look into that on if there's better ways to do like a finite difference compare, for example, is once you've constructed the vector function operators, so say, in our previous example, you finally constructed what this M2 matrix is going to be. These are then callable in a way that you can pass real values in. So you could pass in test points or test cases to at least do point case evaluation of your function to see what it's evaluating at those test points. And you also now have the methods can also be tested. So you could say, hey, return to me the Jacobian and the Hessian of this test point, and you can evaluate those for a quick check.
Okay, thank you.
Yeah, absolutely. Great questions. So the question is, this implies asset doesn't have the ability to handle non-continuous derivatives. And yes, because everything's built of primitives, and when you run SciOpt, natively SciOpt is looking for the Jacobians and the Hessians of your vector function operators. Having something that's not differentiable is a problem point for you get the advantage of running something with analytical Jacobians and Hessians, but you now also get that at least that thing to keep in mind is that you want a solution space that is twice differentiable. Alrighty. So speaking of that, and a good way to handle something like that is with interpolated data. So sometimes you have some data pattern or a data structure that you want to be included in either constraints or an objective function, but maybe the data is discrete, or the data you need smooth twice differentiable operators of that data. So Asset has a pretty robust interpolation scheme built into it that works with the vector function type system. So you can construct what we call interp tables using the vector function interp table 1D call, where you pass in time data and you pass in time history and data outputs of that time history. And essentially those are now discrete points in a table that you can fit a curve to. So you can do a linear fit. So when you define your interp tables, you'll pass in your time data, your vector data. You can declare what axis you're referencing on this. So if it's transpose axis 1, for example, normally you'll just pass in time and data, and then your kind. So what kind of fit do you want this interpolation to be? The default is linear, but you can also pass in cubic, and now you're passing in a structure that is a twice differentiable spline fit of your data. So this is a great use case for things like planet ephemerides. So in day 2 of the training, we're going to use an ephemeris frame, and you actually define the frame and pull discrete samplings of spice kernel data of where planets are, and then do a spline fit of that planetary position so that you now have a continuous twice differentiable function that you can evaluate for where your planets are. Or if you're doing a flight case or a launch vehicle, you can do aerodynamic coefficients where you have now a smooth table that is twice differentiable of something that you need to do table lookups of. So this is a really useful type system that we use a lot for evaluations. You can also use it for something like a rendezvous constraint. On day 2, we're going to do a rendezvous type problem, and you can use a table to essentially populate where your rendezvous target is as a function of time. And now, because you've got that table lookup built twice differentiable, you can smoothly and continuously have that as a constraint or an objective.
What is the underlying interpolation scheme?
So the question is, what's the underlying interpolation? I believe it default mode is to a linear fit, but then there's a cubic fit. So third order fit.
Is it
piecewise? I believe it is piecewise, yeah. Yes.
I got a quick question for you. On the error coefficients you're talking about, are those like 1D type of tables, like, you know, mock versus CA, or can they be multi-dimensional tables, like a function of mock alpha and beta?
Great question. So these
you won't have that space, but
right. So the question is, are these 1D interp tables? So using the vector function interp table 1D, it is assuming one input. You can do a multiple array output. So like the planetary ephemerides, you can do for one time, give me the interpolated x, y, z, x dot, y dot, z dot.
Right.
So you could do something similar. Now, we don't approach it in this training. Asset does have a multi-dimensional table type.
just curious, since you mentioned arrow tables, at least for a launch vehicle, I have multi-dimensions.
Yes. So this isn't the function you use for this is the most commonly used. But for special cases, we do have multi-dimensional table.
And I realize we'd not have, you know, that type of arrow in space. So
yes.
But,
yeah, the drag table, once you're in orbit, is really easy.
yeah.
Yeah. Yes. Yes.
Oh,
Yes. So again, James Pezent's dissertation has an example, a multi-phase launch vehicle example that does use arrow coefficients. I believe essentially from an open source version of missile.com, but he has actual arrow lookup tables. So we've kind of gone through a lot of the core functionality now. We get to now move into the hopefully a little bit more exciting component of the training where you're using that core underlying functionality and doing organization and construction with it. So the most common way you'll use this vector function type system is implementing a vector function inside of a Python function that you call. So you can pass in any constants that are on the Python side, and then any vector functions that you need, you use the argument type system. So in this example on the right, we've got a function implementation. It has 3 inputs that are Python inputs of A, B, C. So these could be integer. Let's assume A, B, and C are all float points. You know that it is 1, 2, and 3. or 1.0, 2.0, 3.0, obviously, to be a float. So you can pass in whatever defined float point data storage units you need in, and then you can allocate operations within this vector or within this Python function that use assets vector function type. So you can say, hey, within this function, we've got these inputs coming from the Python side, but we also want to be able to pass in a size 3 vector function argument. So we'll allocate the size, and in this case, we're using the toList method to break it apart into its scalar components. And then let's say, hey, we want to make equation 1 and equation 2 that are doing vector function index 0, so this x naught plus whatever float point you've instantiated the problem with for A, minus whatever gets passed in as a vector function argument for x1. We do something similar on equation 2, and the result is we want to return a vector function stack of these two equations. So these are both scalar equations, so VF stack is going to return us size 2. So the next step, now that we've defined the function, it's a Python function, we're going to instantiate that function so that the next step is to pass in vector function arguments. So you don't have access to these vector function arguments to this definition. You need to instantiate this function. So we'll say func is equal to an instance of this function call, and we're doing 1, 2, 3 as the Python inputs. So now this func term is a vector function operator that's been instantiated with essentially A is 1, B is 2, C is 3. But you can now pass vector function arguments into this func, and it will continue stacking your operators until eval. Or like we were saying, once a vector function is defined, you can pass real world values into real data stored values into these vector functions, and it'll compute it like it's doing it at runtime. So say we've instantiated this function impl with 1, 2, and 3 for ABC. So now func here has A, B, and C data values locked in, but the args size 3 has not been called yet. So let's call it with a real world example or real world values. So we're going to print call func, and you call it just like a function now, and pass in a list. And this list that we're passing in are going to be the args, the vector function arguments that are being passed in. So now we are saying, okay, we've got an instance of this function under func. Do an evaluation of this asset vector function using 1, 1, 1 as arguments 0, 1, and 2. So the return of this is 1 and 5, which if you go through the math, passing in all ones and the instantiation of A being 1, B being 2, C being 3, it's returning 1 plus the 1 that we instantiated the problem with minus 1. So we obviously get a result of 1, and equation 2 is giving us a x2, which is the last data input to the vector function arguments, times b, which we instantiated as 2, plus x1, so the 1 of the vector function argument, times c, which we instantiated to be 3. So that yields a 5.
So this, sorry, I had a question. How does it know what is inside of args3? Because that's not A, B, or C. So how did it know what's in args3? I don't quite understand that. Is that something built in, or
Yeah, great question. So this is what took me a while to wrap my head around too when using assets. So this is getting used to interfacing with args3 is a little bit of a learning curve, definitely. So we've defined the function. We actually instantiate functions. So if you ever write a function that has args in it, before you can pass values into args, you're going to want to instantiate the function like we do on this line. So this func here is not an evaluation, it's an instantiation.
Mm-hmm.
So essentially func here is just instantiating it with A, B, and C defined. Then, now that it's instantiated, we can call this instance and pass in a list of what we want the args to be. So this function call here, where we're calling func and passing in the list of 111, this is the point in runtime where the function knows args3 is this list of 111, and it then evaluates it.
Okay, so what happened to the 1, 2, 3? Does that just a placeholder?
No. So those 1, 2, and 3 are still being used in evaluation. So for this instance of the function, 1, 2, and 3 were passed in as the Python arguments. So when we run this evaluation passing in 111 as vector function arguments, because we're using func and it's the instantiation func here, we know when this is evaluated, A, B, and C are going to be this 1, 2, 3 that we're instantiated with.
Okay.
It's not part of the 111 thing down there. They're constants that get passed into the function. And yes, when the vector function is actually evaluated by the underlying asset code, then it passes in a single vector. But it doesn't look like that when you first look at it, which is why it makes no sense.
That's a good point. So yeah, the A, B, and C are just constants that get passed in for the instantiation. So say, for example, a slightly simpler example, say you have a function that you don't need any Python inputs, you just want arguments. You can instantiate it with no inputs so that it's just, function impl is open paren, close paren, let's say. Then this instantiation here is just, you still instantiate it and say function impl open paren, close paren, and then you pass in your vector function arguments, which I think on the next slide we have an example of that. Yeah. So if you don't have any constants that you need to pass into the function, you can write it in this way, where it's got 0 Python inputs and expects arguments, and then you'll instantiate your function and then call the instance again. So we'll see more examples soon to hopefully kind of feel out that workflow of how do you interface with args versus interface with constants that are coming from the Python side.
So it's kind of as if there was like a decorator there, and like for people who are more familiar with Python, that this is a function wrapper and args is being passed implicitly, right?
Yes. Yeah. I almost even think of it from a Pythonic standpoint. This is almost like a class def of a function evaluation.
Mm.
And then func is your instance of that function. So once you call func, now it goes from just a set of code written in Python to an instantiated vector function object. And now that we have a vector function object, we can actually pass inputs to it and call it.
Okay, so for your example there, at the bottom, the func 111, that is what's inside of args3. Is that correct?
Absolutely. Yep, you are correct.
Whereas the one above it, when you instantiate it, 1, 2, 3, that's Alpha, Bravo, Charlie.
Yep, exactly.
Thank you.
Yeah, definitely. So if you ever wanted an example case where, so say for a fact A, B, and C are always going to be 1, 2, 3. We just needed to pass it in. You can call this func with different args to evaluate different test points. If you needed to evaluate this function with different A, B, and C values, say you needed this to be, 4, 5, 6, you would actually want to reinstantiate a different instance of that function. So func2 would be equal to func impl of, 4, 5, 6, and then you call func2 and pass in a list of what you want the arguments to be. So we also had some questions in the room.
Yeah. When we instantiate it, does it compile it into C++? Or is it working in Python time?
Yeah. So yeah, when you're creating this func instantiation, it is still never touching. Oh, I don't know what happened there. It is not hitting the Python interpreter. You are essentially just creating a vector function object. So it's still on the C++ assets object side.
View.
Yes.
Yes. Then you're in that. If you want to change the system, then you can use view.
That's a good point.
That'd be a good example.
Yeah. Okay. So Professor Su just mentioned also a good example to help understand this, and actually an example that we will do later today is if you have the circular restricted three-body problem defined in this, the mu, the mass ratio of the problem, would be one of these constants that you instantiate it with. And then when you want to run your position and velocity states to be evaluated, those get passed into the instance of CR3BP as your test point states that will actually get evaluated as args. Can you have multiple args? So no, asset's going to want you to have. Okay, I'm going to say no with a caveat here, where you could absolutely redefine a different arg structure and then use your previous arguments and break those into different allocated args. That is not a use case that we're going to cover today. So if you know that you want 6 inputs, best practice would be let's set your args to size 6 here and just break it apart into subvectors from that. So you're only, when you call this function input, it's only going to be able to handle one arg structure into it. If you want to create a separate sub arg structure within, that is used to user discretion, absolutely. Args is everything.
There was a good question in the chat.
What was the question?
They're asking if you can use bars.
Yeah, so this is still you're writing a Python function, so you could certainly do keyword args or quargs in the instantiation here, as long as those quargs are going to be defined when you do the vector function evaluation. So if you've got a quarg that's not defined when you do the call, it's going to error out just like it would if you were doing a Python operation. Yes.
I've done that.
Yeah, that's a good point. There's
This is all still on the Python side.
right. Good point. So if you couldn't hear in the room, Dr. Stein was saying that he has examples of writing this with star quargs to just handle large input dictionaries, and it's still being handled exactly how it does on the Python side. One more question.
Kind of hint on this with the args. This is something that I talked to you guys about, you and Jamie about. So this, I guess, implementation is kind of like, I'm going to say it this way because it's not exactly, but kind of like just a memory reference row layer type thing, looking into the C side of everything, right? So it's not doing anything at this point. It's just a placeholder, right?
Yes.
So if you have something like this, and let's say you have this as a function and that you want to put like a control law on there. So you want to really have your ultimate thing that the optimization controls or optimization problem will do is like a 6-element vector.
Yeah.
You can define an args. So you can kind of do it a couple different ways, right? So you can do args here as a 6-element vector, but only pull out the first 3 and use the first 3 here for whatever you want to do.
Yeah.
But the other thing is you can also have a function somewhere else that talks about the other 3. And they all point to the same place in the C side, which is not straightforward. Do you remember that conversation that we had?
Yes.
You might want to bring that up just to have them be aware of it because it's complicated. You probably should never do this kind of thing, but it does work that way because that's how you're interfacing into the C level of the arguments like you do on the bottom line, right?
Yes. Yeah. So if you couldn't hear in the room, it was kind of a discussion on the args structure. And again, if James is online, he would recall that this is an analogy, not an actual statement, you can think of args similar to pointers if you're familiar with the C++ pointer. They are not pointers, they are object instantiations. But yes, it's that same logic of an arg itself is not a data storage, and it's not evaluated until you actually pass real values in with this func call. And similarly, you can use args in multiple Python instanced functions. And in the next slide, even, I think you will have a case where you can have a large arg structure in one function, and then you can pass a subset of that large args into another Python function that expects a different sized args and do its computation, and then it can return a VF stack back to you. And because you're not, until you evaluate it with real values that you're passing into args, it's still just using all the vector function type system. So it can stay self-consistent, but be sure to track the sizes of the size and how you partitioned your arguments.
I think the thing that confuses people is that you're not actually evaluating anything when you put these things together. So you're just putting together the calculations that you want asset to do, and nothing actually happens until you push this big shiny red button.
Yes.
So.
Yeah. If you couldn't hear in the room, I want to make sure to reiterate in case the room is quiet. But the comment was essentially that that learning curve is kind of in the fact that it's not actually evaluating this expression until you actually pass in real values or do an actual asset integrate or optimize. This argument structure is how you construct what the problem will do when it's evaluated. So even here, this instantiation of func, we've not done any calculations when we do this. We've now just configured it so that when we pass values into func, it's ready to do these evaluations with whatever arguments we give. And in this case, we've passed in constants from the Python side. So I think this was great discussion. This is where the rubber is actually meeting the road. We're using these data structures. So I think this was good conversation. I think the next couple of slides hopefully will, if at least through exposure, show more use cases of this. So hopefully it starts to make sense on these next few slides. So we even kind of alluded to this in the discussion on that previous slide. You can compose functions that reuse other Python functions with vector function operators. So say we're going to stick with this RTN frame. Say you want a transform vector function. So we are passing in args, and there's no constants that we need to pass in. We are purely trying to make a vector function object with this. So there's no constants that we pass in. There's just 9 arguments. So we can say, okay, this RTN transform function is going to expect 9 arguments. We can break those arguments apart into the first 6 are position velocity as a size 6 vector. And then the last 3 is going to be the control vector. And then again, remember, you can even sub-partition these vector functions because they retain their vector function object type. So we can then say, hey, R and V are actually rv.toList, and we're going to break it apart into the first 3. So this is more for example. In practice, you would probably just break it apart into RV and U. But then when you want to do some operation on the R and V functions, you don't need to rewrite code, to that standard we've all heard. If you're going to do something more than once, make a function out of it. You can do that with vector functions also. So we can have on the left this RTN basis function that we talked about, where it's a vector function that expects argument size 6, and then we allocate position and velocity from that argument size 6. We do all of our vector function operators to define the unit vectors of RTN frame. And then we're returning a size 9 stack of R hat, T hat, and N hat. So we can then say, hey, cool, this is a function. We can instantiate that vector function inside this other vector function we're writing. So this is a way to stack vector functions together. So we'll instantiate that function as an object. And now here we can take the instantiation of this frame basis vector computation and pass in the 6 arguments being R and V. So we know here R and V is a asset vector function. It's not storing data right now. It's just a vector function type of size 6. So we can pass that size 6 function in to be these args6 to create the coefficients. So now RTN coefficients on runtime of this RTN transform function, RTN coefficients are going to be the evaluation of what's the RTN basis vector components from whatever RV values get passed in. Question?
Yeah. So just philosophy here. So whenever you instantiate a function like this, you have to have a priori knowledge of this function RTN basis and know that it will need 6 arguments already. Is that correct? You have to
Correct.
You have to actually look in the code here and understand, oh, by arg6, I will need 6 values. Rather than, in default Python, you're used to looking at def and what's in the brackets, and oh, you need 6 things. And so instead of that, you got to look down one line or whatever into the code and understand, oh, I'm going to need 6 values. Is that a good way to think about it?
Absolutely. That's a great way to think about it, and how to formulate it is because at the end of the day, under the hood, the code that we write for these vector functions is not going to hit the Python interpreter. It's all going to compiled C, which since it's statically typed, we have to have a priori knowledge of the sizes. So asset will throw an error if you're passing in incorrect sizes to these args. So yeah, very good point and observation. We need to know the sizing, and when we're passing in vector function arguments, the size isn't from the Python input to the Python function. It's really what's the size of the args that we're instantiating at the top of that function.
Okay, and so in your big box on the right, when you instantiate it there, you kind of have to know that there's nothing goes in the brackets because all this stuff is defined in the box on the left, the number of arguments. Is that kind of right?
Yes. Yeah. So when you instantiate this larger function, hey, when I evaluate this, whether I'm passing in a list of float points, or if I'm passing in a different, from a structure even above this, passing in more vector functions, this needs size 9 passed into it. And then similarly here, you'll say, hey, I wrote this RTN basis function, and even though there's no Python inputs, I know that it's expecting size 6. So in this case, we're passing the RV vector functions into it. We as users need to make sure this RV is allocated to be a size 6 vector function.
Yeah. Okay. Thank you.
Yeah.
Asset's not going to react to that because it's going to say, sure, Right?
Yes. Definitely.
Looking at those things back.
Yes. So the comment in the room is it is a user responsibility when you're calling and instantiating these vector functions. When you pass something into it, it is on the user to make sure you're passing in the properly sized data to those.
Which ones correspond? So like X corresponds to X.
Right. So the question or the comment on the room is hitting on something that this may be a little bit. I know we're still getting used to this type system. Because anytime you reinstantiate args, it is just expecting some input of size. So say we had a control law we could do control all on the left here, arg size 3, and we can just pass in the last 3, this u vector, this last 3 args as an evaluation because we've redefined args.
But I guess my question is, like, so as an example, in the smaller box, okay, so you're basis, if you flip V and R because of reasons, and then you wrote everything out correctly, would that still work?
Yes. Yeah. However, you can partition this args vector however you want in your functions, and however you partition it, it's just going to take it in order of whatever gets passed in. So if you wanted, for whatever reason, to flip V and R here and then do to list 3303, you could totally do that. Or you could do that on this side, but then you need to correct it here and make sure you pass in V stack R instead of RV. Yeah.
At some point, the C has to know each element corresponds to each element.
Right? Yes. Let's pick back up. We're getting into the bulk of the good stuff of the training now. I know the beginning was probably felt a little dense. Hopefully you're feeling a little bit more at least used to via exposure of how the asset args, vector function args, are used and what these vector function objects are. So we're getting closer to being able to do some more exciting real world examples. So I think we've gone over this slide. So just one more quick rundown. This is an example of once you've defined a function in Python that expects asset arguments, these can be reused and implemented in other vector functions as well. So you can take a larger structure vector function that's, you'll still need to instantiate on the Python side that expects some number of argument inputs, and you can pass those arg inputs. So, RV and U are not data storing right now. They are still just, vector function objects, but you can pass those vector function objects into instances of other sub functions that are expecting arguments of the appropriate size. So with that, we are at a practice time. So I think everybody was able to hopefully get asset installed with the caveat of our Mac support being unofficial. So this is the time to try and put into practice some of these things we saw. So we're going to give a few minutes now. Let's do a test. Try and in a text editor, I suggest doing this in a script because we're going to reuse a lot of these practice problems that we're doing today. Write a Python function. In this case, it will have no Python inputs. It'll just have your vector function arguments. Write a vector function that has 6 inputs and evaluates and returns the result of an arc cosine of the dot product of 2 3-dimensional vectors that you're putting in. So when you think you've got it ready and instantiated, there's even a test point here. So pass in an instance of this function that you write, 1, 0, 0, 1.5, 1.50, and you should get this result to test the function when you write it.
Let's say I define test as so you define test as your function, right?
Yes.
I just defined it as an angle between it, but test as my vector. Let's say I define that as list. Am I going to get an
define
error?
It as what? Sorry.
So test equals that list you gave me, the test point.
Yes.
Okay. We're inputting it as a list, and then it's turning that list into args.
Yeah.
Can I not? Well, should I not turn test into args then put it in?
Yes, you can totally. You can do so. Like func is our instantiated vector function. If your input is a list, I'm not going to use input. If it is a list, you can absolutely just pass a list into vector function.
That's what you're already doing.
Yes. Yeah.
I was thinking before that I had to pass in some sort of vector, asset vector function instead of list itself.
Oh, I see what you mean. So the allocation happens when you pass the computation happens when you pass values to the instance of your vector function.
Okay. I remember you showing that.
Yes, yeah. You don't need to pass in args. You pass in this case, we want a real world value out. We want a evaluation of the function. So we pass in actual points that we want it evaluated on, and it returns the actual result. You are hitting on, you don't have to only pass in real world values that you want evaluated. You can pass in other function evaluations to just stack your vector functions. So like in this previous example, we instantiated a vector function like this, and instead of passing in real world values, we passed in vector function args to get evaluated.
But it's still a list.
Right here, RNV is not a list, it's vector functions. So an instance of a vector function, you can pass in other vector functions or real world values. If you pass in real world values, like a list of float points, it will evaluate that method and return a real world value doing the computations you told it. If you pass in a vector function, it's now just going to say, hey, this is another stack of computation that when I get evaluated, I also need to pass any real world values into this to evaluate it and then manipulate the return of that.
Okay. So
I'll leave it as like an example. You have to feed it a list or a numpy array of the correct size, right?
Yes, it needs to be the right size.
You can't fill it in 6 scalars. They just try to grow.
Okay.
So, but it has to be like a list or a numpy array of the correct size that you feed into that function.
okay. So you tried it as
Like
not a list, but as an individual.
1.100. Yeah.
Okay.
Then just hit it wrong because it's not the right size.
Right. Cool. So I think I got this. I'm a little distracted. Right.
Okay.
Can you go back to that slide you were just talking about?
Yes.
So you said RV is not a list.
Correct. RV in this case, because so X in this example, X is vector function argument size 6. RV is just breaking that into a sub vector. So the toList call on args just results in subvector argument still. So the result of the args.toList is maybe a misleading name in this case, but it's not returning like a Python list structure.
Okay.
It's returning a subvector of your args that is itself also a vector function.
So it's I get it. I think I kind of get it.
It's just slicing it.
Yeah.
Different variable that you, but it doesn't actually do it.
So if I were to say RVU, no comma, is equal to x.toList, same thing. Then would it return a Python list of 2 vector functions?
No, it's still trying to just chop it up into subvector functions. It's not going to return a list. It's going to return just subvector functions.
Okay.
So you need to allocate it as such, as the toList is just going to return to you however many subvectors you're breaking it apart into.
That makes sense.
Cool.
So, quick question. So, what we have, okay. The arguments here, right? So you want arguments from vector functions. There's also an analogous version from optimal control. What's the difference? And if there is a difference, they point to the same thing.
Use vector functions, yeah. You use the args from. So there is. We'll get to that in the next section.
Okay, but there's a difference.
There is an actual difference between ODE args and args. Yeah, we'll get to those in the next slides.
That's all the code that I have is coming. Small.
Yes. Okay, so I hope people could also hear the conversation in the room. Are folks online? Is this making sense? Did that kind of demo hopefully help? Running into any issues?
Hey, Aaron, I had just a general question. So,
Yeah.
if and I get we're looking at the like structures and things like that for vector functions. So, if you don't have any arguments in your defined vector function, is there any advantage to using the args construct?
So just rehashing to make sure I understand, you're saying if you're not using any vector function args, is it better to just assess the
Well, I
like
mean,
a Python function itself?
in your what's on the screen right now, you have the def angle between with just open paren, close paren, and whereas before
Yeah.
we had some variables
Yeah,
to define the
like
functional.
ABC.
So
Yeah.
so if you don't have any of that, if that within the parentheses, if that's empty, is there any real advantage to doing it this way?
Yes. So if you are trying to write something of the asset vector function type system, which, as we were kind of hashing in the beginning, that gives access to the analytical derivatives and the compiled type system, you need to use this args interface. You can't just pass asset arguments in as a Python input. So anytime you're doing an operation, either for a computation or, as we'll see later in the training, you're setting up an optimization problem, you're going to want to put all of your dynamic variables as args so that asset is able to dynamically vary those and change them with derivative information for feeding into SciOpt, the custom-built optimizer.
Okay, so for something as trivial as doing an arc cosine like this level of stuff, I mean, there's no real advantage to doing it this way.
So if all you needed was a Python script that found an arc cosine, yes, you could absolutely just use NumPy. Say you're forming an optimal control problem and there's a constraint you want to apply on this angle between. In that case, you're going to want to write things as a vector function argument, because vector function args can inherently be appended, as we'll see later in training. Any function defined in this format to use vector function arguments can be appended as constraints or as objective functions in an optimal control problem. So if you just need a calculator that just calculates angle between two vectors, absolutely, just write it in Python or whatever language you want. If you want to use asset to optimize a problem and there's some angular constraint on that problem, say you have a solar sail and you want to constrain how far the angle of your pointing vector can vary from the sun line vector, you're going to want to write that constraint as a vector function argument so that you can append it as a constraint to your optimal control problems.
Okay,
and we'll get into that later. So good question. This is all of this practice is kind of unto the later parts of this training where you'll be writing actual optimal control problems in asset. Were there any other issues online? Were people able to get the function written and running, and written, instantiated, and running with the test point? Mm-hmm.
Operations have been broken out, right? So,
Yes.
You have the head, which slices it, and then you normalize that, so that's one operation, et cetera, et cetera. And then you have the dot part of that. What happens when you nest those? Can you nest them and not have a big issue?
Yes. So the question was, can you just nest operations? You absolutely can. So, I mean, in my example case, you could absolutely do this as a one line, not verbose, but yeah, you could. Yes. So because I had forgotten to reinstantiate it, had an issue with this where I just normalize and dot and then normalize again. You can absolutely now do func is test, then run your test point through, and it'll compute because it'll do everything in line. Okay, so I'm assuming no feedback or no comments is good comments. So people were able to hopefully, if you have access to running asset, are able to do this. So let's move on to a little bit more substantial example. And this one we'll try and have you guys, we'll give time for you guys to try and code up a function on your own. And then we'll run it in debug. And then I will again walk through the solution. So this practice case is defining the equations of motion of the circular restricted three-body problem. So I would assume a lot of people are familiar with this, or at least familiar with the terminology. So it's a problem of a third body, normally a spacecraft, in a rotating frame subject to the gravitational acceleration of two bodies. So the two bodies are non-dimensionalized and are passed in and quantified by this mu, this mass ratio term. So in this case, here's an example where you are going to want a Python passed in constant. So write a vector function in Python that uses mu in the Python inputs, because mu is constant once it's declared. But then you're going to need a size 6 vector function argument for position and velocity. And you just, this is an ODE computation, so you just need to return a VF stack. So return 6 elements, which are the derivatives of your states. So you're breaking it, you're going to input an argument size 6 and a Python input 1 of mu, and then write a function that breaks it apart into its subvectors. You're going to need to define these other sub-quantities, which are the distances of your spacecraft relative to planet 1 and to planet 2, and the acceleration from the rotation of the frame for this Q, and then return a size 6 VF stack of whatever you need that is essentially the velocity vector for the derivative of position, and then the derivative of velocity are these operators. So recall D1 is a vector, D2 is a vector, Q is also a vector that you're constructing down here. So let's give a few minutes for that. And again, here's a great chance, flag us if you have questions or run into a sticking point, and hopefully so we got a question in the room on how do you do for the distance computations a vector function and then handle minus mu 0, 0 is a normal vector. That's a great place to remember as a reminder that as long as your sizes are correct, you can add, subtract, and do NumPy arrays with operations with a vector function. So even though R vector is a size 3 vector function, to compute D1 and D2, you can just subtract from R a NumPy array size 3.
That is good.
Definitely. And that's something you'll do often is multiply by a scalar or add some fixed NumPy array, something that's not a dynamically changing vector function, but is still necessary for your computation.
And
so just for everyone online to hear also, one thing we had in the room was the acceleration component. They're trying to do a combination to compute the Q term in acceleration. They were doing a NumPy dot array and then passing in scalar function arguments, so vector functions into that. So to debug that, because that was throwing an error, to debug that, make sure you utilize the vf.stack function when you can, because it allows for mixed types. So if you have vector functions, scalar functions, or NumPy and float points. So the fix was just that Q vector, write it as a VF stack where you're doing the components to result in a size 3 vector. Alrighty, so let's walk through this example now. So you guys likely have a function very similar to this. You might have used different syntax, but if you're meeting that test case, then the evaluation stacking is happening in the correct order. So again, equations of motion, we pass in a mu value. That's a constant coming from Python. The states that we're dealing with, the position and velocity states, is size 6 args. We then partition those states apart into being position vector and velocity vector r. So now these are size 3 vector functions. P1 location, you can just compute the that as a NumPy array. And remember, we can do mixed object operators of vector functions with NumPy arrays as long as they're proper size. So for relative position, you now can just do the position size 3 vector function and subtract off the NumPy arrays. Then for the planar elements, we can even break apart R and V even more into Rx, Ry, Vx, Vy. Gravity terms now, again, it's your mu minus 1 times D1 normalized power 3. So that means we're multiplying it by the D vector and then dividing it by the magnitude of D1 raised to the cube. Same thing for the gravitational component 2. You take your mu term, negative mu term, and then do D2 normalized power 3. So here we're getting to kind of see the advantage, or why we have the precompiled types of like normalized powers, is you can do something like this, and in one line with a precompiled object, you've got this evaluation. Q, like we had said on the one error that we debugged that was happening in the room, you do a VF stack because we can mix data types in VF stack, and we do the scalar operations for index 1, a comma, do the other scalar operations, comma, and then just a 0, 0, 0 float. Then your total acceleration, you can just do vector sums. So it's going to sum the vector components together. And finally, return your equations of motion, stacking the velocity and the acceleration. So hopefully this was an example. We've walked through the structures. We've given a few examples, arbitrary examples. Hopefully this is a more concrete example of defining a vector function that takes in your argument structure and then does relevant mathematical operations on it and then returns a value. Yeah.
Stuff that we can do. That last VF stack is fed as a list.
Yes.
If I feed a list into that VF stack, problem. If I put the one from the definition of Q, it does not like it. And it throws up as it's an unknown type, blah, 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 blah. Which I don't know if that has to do with that 0 being just 0 and you get a vector scalar or something like that.
Yes.
It's weird. And so I can run it if I have 2 lists into the VF stack, it breaks. If I took the first one out but has the second one, it's fine. And if I take both of them out, it's fine.
Yes. So the question is about the VF stack, passing in just terms versus passing in with the bracket, so a list.
Yeah.
I will follow up on that question. I believe that if you're going to do brackets for a question, for a list input, they should be the same type within that entire list. So if you do VF stack without a bracket, you can do this type mixing like we see here, where you've got vector functions and float points. If you use the bracket, I think it needs the same type, but I'll follow up on that. Yeah. Any questions online? Okay, so we've got one more example that we're going to run through here. This one's slightly more complex, where we're now going to use a vector function input or an argument input of size 9, because we're going to need our position, our velocity, and a u vector, a control vector. So essentially, we're modeling the two-body problem. So you have a gravitational body attracting at the center of your frame, or at the origin of your frame. I did actually put a mu value for that one. So your Python inputs will be the mu value, the acceleration of your two-body, and then alpha, which is going to be a scaling term applied to how much thrust your u vector is applying. So this one is going to be an args 9. You're going to want to partition those args into 3 vectors, so r, v, and u vectors. Your Python constant inputs will be mu and alpha. So then again, we're trying to do, and this is a differential equation. So what you're returning is just the derivative of your position and velocity states. So for position derivative, it's just velocity, quite simple. For your acceleration, you're going to have two components. You're going to have the ballistic two-body problem example here, where you've got that constant input mu. And then if you're picking up on getting more used to the syntax, this right here should probably look like an R normalized power 3. And then you're going to have a control vector. So we can build M as we're going to get the RTN components. So the RTN frame, which is just a function of your position and velocity doing vector operations. You can then construct those into a column matrix and do matrix operations of that transform matrix times your U, because notice your U vectors are in the RTN frame. So bonus points on this problem also, if you recall that we can stack other smaller sub-functions that expect vector function arguments. So if you recall from our previous examples, we had a function that just derived the unit vectors of the RTN frame. You could write one function that just expects arg6 and computes RTN basis vectors, and then you could the return of that, use that to construct your transform matrix.
You construct the M matrix there.
Mm-hmm.
The various parameters that are anti-hat and pret and hat are obviously reading MATLAB, right? So that would be rows, like row vectors for me, right?
Yes.
So
yeah.
How do you tell this thing? I mean, I remember we have the BF dot row matrix. Is that how you tell it that it's a?
So this
passing in rows, or does it just?
In this one, you're going to build a column matrix. So because it's remember, columns are your you can do basis vectors versus as rows or as columns. So recall from our previous example, we had, did I go past it? No, I passed it. Okay. From our previous example, we did a RTN 18. Yes. There we go. Sorry. We did an RTN basis function, basis vector function computation. Then that return, you can instantiate and get your coefficients and then turn into a row matrix. Sorry, it is row. Yes, sorry. The notation, you're correct. The notation shows a row matrix.
N hat dot cross R.
Mhm.
You didn't really have to do, you're not doing N hat dot cross R hat. You're doing cross R. That's where you're normalizing it again. Or you could have just like N hat dot with R hat.
Yes,
Right.
you're right. Yeah,
Either way.
yeah,
Then you don't have to normalize.
yeah, true.
This sometimes it's also useful to, especially the first example, show it. I know it's harder.
Yeah,
You're talking, you're coding, you run into problems.
yeah. Okay.
That's-
Live demos more.
Yes, live demos help,
Okay.
especially the first couple when people are getting used to the syntax.
Yes. Yeah. That's true. I'll also clarify to the question in the room. You can construct this as a row or as a column matrix, but just make sure that your sizing is consistent with how you formulate your U vector. So I believe by default, you're actually in this case going to want a column matrix because it's going to import U as your vertical, or you can do a row matrix times U transpose.
Right. Wait, oh, disappeared. U is going to get allocated to training, essentially. It's a vector. Right, U matrix on it. Yeah. So is it row matrix or column matrix? Oh, okay. You'll by default do column matrix. Okay.
That makes more sense.
Yeah, because that's also asset has to default to one of the two, and it defaults to column matrix. So
Right.
kind of set to handle its defaults.
Yeah. Okay.
Yeah. So I apologize that the notation here I probably could have made clearer.
Oh, that's all good. Yeah. As long as I know what it is, it's easy to work with.
Yeah. Okay, so I think we've got people being able to replicate the test point in the room. Anyone online able to finish it? Anybody struggling with it?
Ask questions.
Any questions, any errors? This definitely meant to be interactive. I think hearing nothing, we'll keep marching on then. So we'll walk through the solution to this. And then what time is it? We're at the end of this slide set. So let's go through this solution. So perfect. Okay, so this one was a little bit more complex than that last one. But again, we've got two Python inputs that we passed in, the gravitational acceleration and this alpha scaling term. And then size 9 vector function args. We partition those apart as position, velocity, and the control vector u. This code, so in the meeting invite, you should have been given a zip file that's also that's titled the asset training user inputs, I think it is. That has all of the code base used in creating these examples. So here we reuse that RTN basis and reuse that RTN basis function that we showed earlier in the training. So if you went this route and had a separate, went for the training bonus points and had a separate mode that calls an external function to compute them, you can verify that and look at the solution in that zip file. So we instantiate that basis function vector that we showed earlier. We then find the coefficients by actually passing in the R and V vector functions into that function to return the 9 elements of the RTN frame. We construct a column matrix with those elements as 3 by 3 because remember, the function is returning us all of the R components, T and then N. So since we're given those, we want to construct a matrix as columns so that we're doing proper multiplication with our control vector. So create the column matrix, and then the acceleration term is exactly like we said. The two-body acceleration is just about as simple as can be. It's minus mu times r normalized power 3 to capture the ballistic motion of the two-body problem. And then we're adding to it this float point of alpha that we instantiate times the matrix multiplication. So we've now got a asset matrix object. We're multiplying it by the u vector function, resulting in a vector, proper sizing for a vector. And because it's proper size 3, this is size 3, we can just add those two vectors together, stack them into an output size 6, and return it. So hopefully those of you online definitely speak up if not, but it seems like at least in the room, everybody's been able to replicate the test point. And this is probably a good exercise to show.
I don't know.
We'll debug. This is a way to show that there's a lot of different ways to slice a problem that still stacks the proper operators and returns what you need. So this does conclude the first slide set. So this is concludes the introduction to vector functions.